topic, we're going to be talking about external bibostability. But in order to get into that, we need to talk first about signal measures and operations. So we have a signal, which is basically a function of time. And so given a signal, how do you measure the size of the signal? One size or one measurement does not fit all. So for example, think about the size of a person. For example, what do you mean by size? Do you mean how tall are they, or how wide they are, how fat, heavy they are? What do you mean by size? So when you say large, a large person, what do you mean? Do you mean a tall person? Do you mean a fat person? So there are different ways of measuring. One size does not fit all. So how do we work with these? Now, some measures can be used for a large class of signals. And so in general, we're also going to consider both a measure and a space of signals that meet some specifications. We'll talk about that. So first of all, here are some signal measures. The simplest one is the infinity norm, which is basically the supremum. So for a signal W, the infinity norm is the peak magnitude of all the components over all time. So the supremum over T of W of T, the infinity norm of that vector. So in general, this may be a vector. So by way of example, here is an example, Wt, which is in this case a scalar. And we can see that as t goes to infinity, this term goes to 0 because t gets large and this denominator gets large, so this guy goes to 0. But for any value of t, at no value of t is this equal to 1. That's why we use the supremum as opposed to the maximum. The supremum exists even if the maximum does not exist. So the supremum is reached asymptotically. All right, so that's the signal measure. It's a bounded signal. A signal this is the bound on the signal. So if there is a bound, that's the infinity norm. And so you actually are looking at the bound of every component in the vector over all time. That's the infinity norm. The 2 norm is often referred to as the square root of the energy of the signal. And so in discrete time, we can write it this way as the sum over all time of the vector transpose times itself square root. For continuous time signals, we have the integral over all time of the vector trans. So this is like the 2 norm of W integrated over all time, 2 norm squared integrated over all time square root. So this is the 2 norm. Associated with the 2 norm, we also have this inner product we've seen before. For discrete time, we have x transpose times y. We sum the elements, and in this case, we would actually sum for a function of time. We would actually sum that over all time. So this is the vector inner product, and then we sum over all time. In continuous time, we have the vector inner product, and we integrate with respect to time. And so now we can recognize that the 2 norm is an induced norm. That is, it is induced by an inner product. We can also talk about these quantities, the autocorrelation matrix. So this is how the function x relates to itself over all time. We take the limit as t goes to infinity, 1 over 2t. And so if you notice that the integration goes over an interval of 2t. And so this is the autocorrelation matrix. The spectral density is the Fourier transform of the autocorrelation matrix. So in order for this to actually make sense, the Fourier transform must exist, which means the signal must be finite over all time. So this is the Fourier transform of it, and so we have the spectral density of it. Those are just signal measures. These are not norms. Okay, these are not norms. These are just measures of signals. We can talk about the RMS value, root mean squared, the root of the average of the squared signal. So we first square the signal, and then this takes the average. Again, it's over 2t. We're going from minus, so this is basically over a period of 2t, and we then take the limit as t goes to infinity of this quantity. When we're all done, we take the square root. So this is basically computing the average over all time. It's kind of like an average of the square. So this is what it is in discrete time. We have a summation. In continuous time, we have the integral. We can also define what's called the average power of the signal, which is the instead of having the square root, it's just that quantity squared. So it's this quantity without the square root. So by way of example, here if I have a periodic signal like this pulse signal, a pulse width modulation signal. Okay, so the period is P, and it is on for delta times P, where delta is between 0 and 1, and it's off for the rest of the period. And I can go through and show then that for this definition of the power, that for this signal, P is delta. Okay, so the power is given by delta. So we have that. The one norm signal is often called the action signal, and it is basically the vector one norm summed over all time for discrete time, or the vector one norm in continuous time integrated over with respect to time. It's this signal, the one norm, is often referred to as the total available resource. In general, we can talk about the p norms, just as we had p norms for vectors. We can talk about p norms for signals, for vector valued signals. So if w is a vector function of time, we can define the p norm as the instantaneous vector value, p norm, raised to the pth power. So remember, this is equal to the sum of the absolute values raised to the pth power. Okay, and ordinarily to actually compute the norm, we would do 1 over p, but now we're just not going to do the 1 over p yet. Then we sum, and then we do the 1 over p. Okay, and in continuous time, this is how we defined the p norm for a vector valued signal. Okay, so we have those definitions. We can also, so those are actually important norms that we'll use a lot. Some other norms that are sometimes used is, this is the average absolute value, the limit of the supremum of this quantity with one norm, or in continuous time, instead of the summation, we have the integral. So we often have this 1 over 2t that kind of does an averaging. So average absolute norm. Okay, so it's kind of like RMS, but with one norm instead of the two norm. And we have relationships between some of the various norms. So the average absolute value norm is less, in general, that number will be less than the number that you get for the RMS value, which is in general less than the infinity norm of the signal. And also we have that the RMS value is less than or equal to this product. So we have that relationship. And again, for vector signals, we also have, so these relationships hold for scalar signals. For vector signals, we have these relationships. Okay, so instead of just having AA and RMS, we now have these n, 1 over root n, and so forth. So we have signal measures. We have ways of capturing the size of a signal. And as you see, we've actually just shown you an infinite number of measures for signals. For example, the p norm, anything from p equals 1 to infinity will work. And and then we have some other signals. And so depending on the type of signal that you're working with, one or other of these measures would be useful. Stay tuned and we'll talk about signal spaces.